Application of FFLGN membrane as a humidity sensor and comparison of its performance. This section provides an overview of application of humidity sensor based on graphene oxide, FFLGN membrane, and other carbon materials. In turn, these materials are durable and have high thermal conductivity as well as excellent absorption characteristics. Therefore, they are important practical application as a humidity sensor. The membrane based on FFLGN duo compared with other carbon materials contains functional groups such as hydroxyl, carbonyl, and carboxyl on their basal plane, and this makes it hydrophilic. Further, sensors based on such materials are moisture sensitive. Further, according to the above listed properties, FFLGN is currently an important material for creating humidity sensors with high sensitivity, which is necessary for such fields of engineering and science as medicine, textile industry, agriculture, biological products, scientific and technical centers, food industry, and other industries. To create humidity sensors, the most important electrophysical characteristics are faster response and short recovery time, stability of work at various levels of humidity, and in aggressive environments, wide range of moisture diffusion, as well as most important are the easy of manufacturing technology, low cost, which are necessary to satisfy consumers to achieve above listed characteristics. Over the years, much attention has been paid to the creation of various types of sensors with high sensitivity based on such materials as metal oxide nanowires, ceramic nanomaterials, silicon and semiconductor nanoparticles, etc. But despite this, the creation of sensors with above listed characteristics remains an unsolved task to this day. In this regard, as the initial material, we choose FFLGN membrane, which is one of potential materials to satisfy the above characteristics, and the choice of suitable material is considered the most important factor in creating sensitive sensors due to the physical, mechanical, and important electronic properties of graphene and graphene-like materials. There has been more researches and many studies have been done on the creation and use it as sensors for determining various gases and humidity. The use of graphene in sensors for the determination of various gases was first demonstrated in work. Then its related structures such as FLG, GO have become more investigated and used to create nanoscale sensors. Humidity sensors using graphene structures were created for the determination of NO2, NiH3 and CO2 gases, which were demonstrated on the basis of following materials and principles of operation of thermally reduced graphene, epitaxial graphene, carbonate nanotubes, and graphene. Coarser-grained duo thin film, FLG, microscale capacitive humidity sensor based on duo film, high proton conductivity duo, capacitive humidity sensors based on the electrospan PVDF, graphene membrane. We made a comparison of performance of humidity sensors based on FFLGN with similar types of humidity sensors. According to the following characteristics: dynamics of response and recovery, humidity detection range, according to the table, compared to the sensors listed below. Our devices has an advantage in response and recovery time, which has the same time of 360 seconds, as well as a wide range of humidity from 5 to 100%, and its electrophysical characteristics presented in next sections. All the sensors listed the longest response and recovery time 1200 seconds. Besides this long recovery time, 2300 seconds is shown in work, and in the same work the smallest response time, which is 50 seconds, compared with our sensors. A wide range of humidity detection, 0 to 100% is shown in work, and a narrow range to 20 to 36% in work. The disadvantages of these devices are long response and recovery times. Table second shows characteristics of humidity sensors as graphene and its related structures based on the above listed works, as well as due to physical mechanical properties, have found potential practical applications as humidity sensors, and today considered as promising materials in electronics and technology, and particular for the creation of sensitive elements. In this regard, we created a humidity sensor based on FFLGN membrane and determined its electrophysical characteristics, which are discussed in the next section. In comparison with different sensors, the sensor presented by us is a potential device for commercial available product that has such advantages as a wide range of humidity, fast response and recovery, low cost, does not require high technology, and is resistant to aggressive medium. Conclusions for section. First, there are two types of functionalities of graphene: chemical and non-chemical. Both categories of functionalization contribute to change in the properties of graphene, but the most effective is a chemical modification. FFLGN is important precursors for the large-scale production of graphene, which is implemented using chemical or thermal reduction processes. There are four main methods of synthesis of FFLGN: Staudenmayer, Hoffman, Hammers, and Tower, but the most effective is the Hammers method. It is stated that graphite and FFLGN have a layered structure. Also, compared with graphite, FFLGN contains functional groups with high oxygen density, such as hydroxyl and epoxy groups, and on its basal pan, and on its edge with less carboxyl carbonyl and phenol, lactone, and quinone, which contribute to expand of interplanar distance and also makes it hydrophilic. Changes of combination of ID and IG bands of Raman spectrum dependencies on the size of sp2 hybridized zones with low and high defect density modes provides a suitable theoretical explanation for the observed behavior, and allows us to estimate that the size of graphite zones decreases to 1 nanometer during sedation, as well as in other studies on the size of sp2 zones in FFLGN thin films and bulk FFLGN samples obtained by the Hammers methods reaches up to 2.5 to 6 nanometers. Computational simulation becomes a very effective research tool for better understanding and study of physical and chemical properties of FFLGN to solving a difficult problem for experimental research and the proper interpretation of data. Also understand about stable atomic configurations of graphene functionalized with individual atoms of different elements. Basically, the changes of optical, electrical, mechanical, and other parts of FFLGN depend on the functionalizations, that is, on the amount of oxidation, as well as one of the method of synthesis, which can fundamentally change the electrical properties. Also depends on the reduction processes of FFLGN at different temperatures. Compared to the other types of sensors, our device has an advantage in response and recovery time, which has the same time of 360 seconds, as well as a wide range of measurable humidity from 5 to 100, and its electrophysical characteristics are presented in the next sections.